Swayam Prabha. Digital India. Educated India.
So, good morning everybody. Today we will be discussing on the another module of this course, Advances in Welding and Joining Technologies. So, that is related to that welding metallurgy. This is also a part of the complete course, and the purpose of this covering this welding metallurgy is that probably some metallurgical understanding or some reactions happening during the welding is helpful to decide the type of welding processes, or sometimes this critical analysis of this welding metallurgy also necessary to avoid to produce some kind of defects in during the fusion welding processes, or as well as other solid state welding processes. So, we will try to get some basic idea metallurgical aspects related to welding processes. So, this module welding metallurgy we will try to cover that first is the we will try to look into that chemical reactions that is happening in welding process. Second is the one of the most intricate part of welding, that residual stress and distortion, that is the most serious problem happens, and of course, this residual stress and distortion having the link with the metallurgical changes that happens during the welding process. And then we will try to basic fundamental understanding on the solidification and in specific to welding processes, and what are the typical weld microstructure and what is the nature of the microstructure actually developed during the welding process, and probably how we can control this weld microstructure during the process, so that we can expect some desired properties in the final weld joint. So, that microstructure is more related to the weld joint property. So, it is very much indeed is needed to know some idea, basic idea about the weld microstructure. Then we will try to look into that phase transformation happens, is maybe the solid state phase transformation, or what are the consequence of the when there is a solidification happens from liquid phase to the solid phase during the welding process, and how this phase transformation actually affects the final or influence the final weld joint. Then we will try to look into that specifically the formation of the cracking, and in very specific to the solidification cracking, that is the most severe problem in the welding of a specific in presence of the specific components within the weld. So, that is why we will try to look into that solidification cracking in that happens during the welding process, and finally, some basic idea that heat treatment of the weld joint. So, we have the idea about the heat treatment processes, but we will try to look into that basic things is heat treatment, how it is possible to apply in case of specific weld joint. So, with this I can start with the several components of this module. First will the what are the chemical reaction that happens during the welding process. So, that if we look into that chemical reactions basically happens during the welding process. So, we will try to look into the basic aspects, that what are the effect of structural changes happens during the joining of the similar and dissimilar materials, and that structurally changes due to presence of or using of different type of shielding gas or any other kind of shielding to the molten whirlpool, and then how it react with the molten whirlpool and making whether it helps or in to some helps in microstructure formation, or it may not help in the microstructure form, but helps in other aspects also. Second, that definitely we know that weld quality, that means final weld joint in terms of joint strain, their mechanical properties of the weld joint, that is the mostly we are interested, and the life of the weld joint, that definitely depends on the welding metallurgy. So, that is why it is necessary to study this welding metallurgy and how this welding metallurgy depends on the several parameters involved in the welding processes. Third point is that selection of the proper shielding medium, it is also necessary, that that selection of the shielding, anyway shielding gas is obvious necessary to use in the welding processes, but proper shielding gas is need to choose, because it actually finally affects the formation of the different types of weld defects. And suitable welding processes or suitable pre-measurement of the workpiece sample, so that it will finally try to reduce the residual stress and generation of any kind of the distortion. Anyway, in fusion welding processes always it is subjected to some amount of the residual stress and distortion. We cannot avoid this. Only what we can do, that we will try to reduce the amount of the residual stress and distortion, or if the residual stress is beneficial to some extent, that we will try to maximize that component, but most of the cases residual stress is basically not favored in a life of the weld joint. So, that is why our objective should be always to minimize the amount of the residual stress generation, and of course, the amount to reduce the distortion, because distortion is basically affect the dimensional accuracy of the two components when we are supposed to join. But all these aspects is mostly influenced by the solidification mode, or maybe the final weld structure or final microstructure of the weld joint. So, therefore, microstructure, actually formation of the microstructure is highly related to the whether we can get very sound weld joint or not. So, therefore, that study and the effect of the different process parameter is actually necessary, because the microstructure can be developed in the fusion zone and that microstructure can be controlled. So, there are several control mechanisms, so that we can control the microstructure, and indirectly this microstructure also affects the generation of the residual stress along with the other conditions, but the distortion residual stress also influenced by the presence of the microstructure. So, that stress generation, distortion and formation of the microstructure, they actually linked with respect to each other. Therefore, they are interactive phenomena, it needs to investigate or needs to know here, but it is not possible to cover in details analysis of all the microstructural phenomena in this module. We will try to look into some basic concept that generally happens during the welding process, so that we have some idea that nature and type of the microstructure can be developed in the welding processes, and of course, that we can link the different type of the process parameters or microstructure, what is the in terms of the or that influence the amount of the residual stress and distortion. So, in that respect, first we will look into that what are the chemical reactions in welding is generally happens. So, broadly we can categorize the during the overall, if you look into overall all the type of the welding processes. So, we can use that gas, basically shielding gas, to protect the molten pool. So, therefore, we need to know the interaction between the gas and molten oil pool, or when the molten oil pool becomes solidified, how the what is the reaction happens between the these two components, that is also need to know, and this is the one way. Another way to protect the molten pool is the in terms of the using the some slag. So, therefore, slag metal reaction also important to know, analyze, to know, to finally to that influence the weld joint strength. So, these two mode, either using shielding gas or either using the slag, probably the purpose is to protect the only the molten oil pool during the welding processes. But why it is important? Because high temperature during the welding involves, fusion welding specifically, they involve high temperature generation. So, that high temperature, the chemical actually it promotes the chemical reaction with the surrounding atmosphere. So, when it reacts with the surrounding the molten oil pool reacts with the surrounding atmosphere, because tendency increases even at room temperature to at very high temperature. So, that probability is the entrapment of the gas can be dissolved in the oil pool, and they can create the porosity or kind of hole or kind of some other defects, or there may be the they can form the some inclusions also when it is when the molten oil pool react with the outside atmosphere. So, therefore, this type of interaction or this type of chemical reaction of the molten oil pool with the surrounding atmosphere can be controlled by the way using the proper shielding gas or using the proper slag material, so that it will be able to protect the molten pool during the welding process. So, other way also that this chemical reaction can be reduced simply by cleaning the base metal, because most of the cases we can find out the layer of the metallic oxides, and of course, we use the several electrode during the welding process. So, before using that, if we clean the workpiece surface and the electrode material, probably we can reduce some amount of the contamination of the molten oil pool. So, finally, because finally the chemical reactions is basically affects the final oil joint properties, or it can alter the oil composition. It becomes the part of the oil composition, or becomes part of the final composition of the oil joint strength, and that actually indirectly affects the mechanical properties of the oil joint. So, that chemical reaction find out that first some investigation has been carried out, that I think if you look into that reference, Aerokin actually first investigated what is the effect of the shielding gas in welding processes. So, he conducted the experiments on low carbon steel without any shielding gas, simply creating the arc, but with no shielding gas the weld was conducted, and then the properties difference in the different properties we can tabulate it in the here, that mechanical properties. If we see the tensile strength, base metal, what is the range, I think Newton per millimeter square, 390 to 440, but weld metal without any shielding gas found out that there is a decrement of the joint strength 334 to 390, and there is a considerable decrement of the ductility of the weld joint, and of course, toughness, there is a huge reduction in the toughness of the weld joint. So, there is a degradation of the weld joint properties as compared to the base metal if we do the welding without any shielding gas. So, that is why shielding, there is a necessary to use some shielding gas to protect the molten pool. Here if we see that high oxygen, nitrogen and mainly the oxygen and nitrogen content was found in the weld joint. So, around 0.7% oxygen and around 0.2% nitrogen actually found out with the plain oil metal if you do not use any kind of the shielding gas. That means, during the welding process at this high temperature, the molten oil pool actually react with the surrounding atmosphere, and then oxygen and nitrogen actually absorbed within the molten pool or mixes within the molten pool. So, definitely this amount of the oxygen and hydrogen usually comes from the atmosphere, or there may be other source of this contamination or present there is oxygen and nitrogen that may come also from the moisture, that moist air can come from the moist air, or that base metal surface and the dirt on the base metal surface, sometimes we use some the chemical agent on the base metal surface. So, that can be a source of this oxygen or nitrogen, and finally, it reacts with this the oxygen. So, definitely oil metal exhibits a much amount of the lower ductility, and the impact toughness also very low in this case. Therefore, this investigation tells us that of course, we can do the welding process can happen in absence of the sealing gas, but we have to compromise with the degradation of the different weld joint properties. So, in that case it is essential to use some amount of the sealing gas, and even it is possible to using the sealing gas that the weld joint properties is as maximum as of the basic properties of the parent metal. So, therefore, this investigation actually indicates that there is a need of the using the sealing gas in the welding processes. But if we look into the overall effect of the nitrogen, oxygen, hydrogen on the weld joint quality, because these three components in the atmosphere or surrounding atmosphere mainly becomes part of the final weld joint. So, they are having some impact on the weld joint quality. So, in overall if you see that if you look into the steels, that steel presence of nitrogen actually when it is contaminated to the nitrogen, it increases the strength, but reduces the toughness. So, increases the strength, presence of the nitrogen increases the strength of the steels because there is steel containing of the other alloying element. So, that increment of the strength actually depends on the nickel and chromium ratio presence in the different graded steels basically. So, that this is the effect of the nitrogen only, but of course, they are in presence of other alloying elements also important. In general, presence of oxygen in steels basically drastically reduces the toughness, but improves it, that means toughness can be improved if acicular ferrite is promoted. So, we can control the solidification process in such a way that acicular ferrite is promoted, then probably the toughness can be increased even in presence of the oxygen. That means, even it is contaminated with the oxygens. Hydrogen basically the role of the hydrogen in steel during the welding process is try to induce the hydrogen cracking, that is normally we can say that it is a cold cracking process. So, basically these are the role of the nitrogen, oxygen and hydrogen, and in presence of that what types of the properties can be affected when you try to weld the steels. Now, austenitic or duplex stainless steel. So, austenitic stainless steel and duplex stainless steel basically the most influencing parameter is the nitrogen here rather than oxygen and hydrogen. So, basically in presence of nitrogen, the austenitic or duplex during welding of austenitic and the duplex stainless steels, that actually reduces the ferrite content and provides the solidification cracking, or we can say the hot cracking. Basically, chances of the hot cracking actually enhances in presence of nitrogen during the welding of austenitic or duplex stainless steel. Then aluminum, definitely when you try to weld the aluminum, most serious problem is the formation of the react with the oxygen and formation of the oxides. So, that oxides can be trapped within the molten pool and becomes part of the final weld joint as an inclusion. Therefore, in welding of the aluminum, the contact with the oxygen is better to always avoid, because oxygen has the high affinity to react with the aluminum specifically, and this affinity increases with respect to the temperature, and so and forms the oxide. So, that is the one serious problem welding of the aluminum, making the aluminum oxide, and other hydrogen is also having effect during the welding of the aluminum, that it actually forms gas porosity and reduces the strength and ductility. So, when there is a presence of the gas porosity within the final weld metal component or final weld joint, that trapped porosity actually reduces the mechanical properties like the strength properties and of course, the ductility. And other material, specifically the titanium. So, titanium is also having when it interact with the oxygen and mainly oxygen and nitrogen. So, presence of hydrogen is little bit affected in the titanium, joining of the titanium and their alloy. So, that is more serious problem in case of welding of the titanium, and it is a very proper shielding is required to avoid the interaction with the oxygen and nitrogen from the atmosphere. So, probably it is more serious problem the shielding as compared to the steels, or probably as compared to the normal steels component. So, sometimes in welding process also practically we have seen the welding of the titanium links, the extra shielding gas is sometimes required simply to protect the molten pool, because it is having very high affinity to react with the oxygen and nitrogen, and basically when it react with the nitrogen molten titanium, that actually increases the strength but reduces the ductility, or we can say that sometimes it actually decreases the strength as well. Even for oxygen also it increases or decreases the strength, but definitely reduces the ductility. So, we can see that of course, almost all type of materials, ferrous, non-ferrous, that during the welding process they are having the tendency to react with the surrounding atmosphere, and most of the cases we can find out they actually reduces the mechanical properties in presence of these different atmospheric elements. So, therefore, to protect this all these elements from the atmosphere, we generally use the shielding of this molten pool in a different way. Some overview on these things, the effect of the chemical reaction in oxygen in welding, and here we can see that oxygen and nitrogen levels at the during the welding process, we generally find out the different welding processes, the what is the x axis and y axis. X axis represents the nitrogen position and y axis represents the oxygen component, percentage of the oxygen component. And here you can see that submerged arc weld, in case of submerged arc weld, presence of nitrogen component is less during the welding process, but presence of oxygen content is more here in the submerged arc welding process. Probably in submerged arc welding process we can use the slag material or we can use the some flux material, and that flux, one of the component of the flux may be the oxide. So, that oxide is a supplier of the much amount of the oxygen presence in the weld pool, but the nitrogen level is very less in submerged arc welding process. If we look into the gas metal arc welding process, here also oxygen content is little bit more as compared to the gas tungsten arc welding process, because gas metal arc welding process sometimes commercially we use the shielding gas as a carbon dioxide. So, that carbon dioxide basically react at the high temperature, it can form the oxygen, and that oxygen can be a form of part of the final weld joint. So, GTA welding, the relatively the oxygen level and the nitrogen level is relatively less, because in this case we do not use any slag and we use the inert type of the shielding gas. In this case, the inert type shielding gas actually protect the molten pool from the outside atmosphere, and even that inert gas also do not try to react with the molten weld pool. So, that is why argon shielding gas used in case of the gas tungsten arc welding process. So, that the oxygen content and the nitrogen content in the final weld joint is very less in this case. Shielded metal arc welding, we use the shielded metal arc welding some coated electrode. So, here that molten weld pool is basically protected by creating the slag as well as the formation of the fume or gas basically. So, that protect the molten pool, but in this case here the composition of the coating on the electrode, that actually that can be different composition, and that can also act as a source of the oxygen also, and that oxygen can be become part of the final weld joint. So, it is a moderate type of oxygen and nitrogen content we can find out in case of shielded metal arc welding process. But if you look into the self shielded arc welding process, so in case of self shielded arc welding process, in this case it's a resembles that it creates the arc like gas metal arc welding process. There is a continuous supply of the electrode. In case of shielded metal arc welding process, self shielded arc welding process, but this use not any kind of coating on the it use the coating of the electrode, and that actually protect the molten pool, but it is some very little difference with respect to the shielded metal arc welding process as compared to the and as well as compared to the gas metal arc welding process. So, here shielded metal arc welding process we can find out that moderate amount of the oxygen content may have, but nitrogen content becomes more in this process because of the process itself. So, although we can use the shielding gas and different type of protection, we can use the flux also to protect the molten pool, but till in the final composition of the weld joint may have some amount of the oxygen and the nitrogen, and that different welding processes, what are the typical content of the oxygen or nitrogen, some idea we can get here. So, overall we can see that overall all this process we can find out the least amount of the oxygen hydrogen content, probably we can find out in case of gas metal arc welding process, and we can find, but maximum amount of oxygen content we can find out the submerged arc welding process, and maximum amount of the nitrogen can be find out the self shielded arc welding process. Of course, this amount of the oxygen nitrogen content not only depends only on the shielding gas, but it also to some extent depends on the what type of metals we are just trying to weld. Now, protection medium in common welding processes, we can use the different protection medium for the different type of the welding processes. So, first is the gas protecting or shielding gas we can use normally in case of the gas tungsten arc welding process, gas metal arc welding process and plasma arc welding process. Slag we can use that submerged arc welding process, the weld protection medium slag, actually they when using the some flux, metallic oxide and other composition, and after welding the lighter weight slag is comes to the upper side of the weld pool. So, slag this actually protect the molten pool in case of submerged arc welding and electro slag welding processes, and we can use both shielding gas as well as slag. Both this type of protection we can find out in the shielded metal arc welding process and flux core arc welding processes. And of course, we use the protection medium in vacuum in case of the electron beam welding process. So, when electron beam welding process has been done this under the vacuum, so not necessary to use any kind of other shielding medium. So, that under the vacuum there is no chance of the reacting the surrounding atmosphere. So, electron beam welding process we can use the vacuum. So, that is the I think the most efficient protection medium in case of electron beam welding, that is that considers the under vacuum. Another case is the self protection, and that in that case the self shielded arc welding processes we can use the self protection medium. So, that also comes the simply coating from the creation of the arc, and there may be some coating on the wear. But if we look into the laser welding also, sometimes laser welding we use the shielding gas also, normally we use the argon shielding gas even in case of laser welding also. So, all type of welding processes to some extent we can use some protection medium. So, overall look into that gas arc welding we can use the either argon or helium, because using this under this shielding gas they can create the arc should be stable. So, argon and helium in case of gas will be the most suitable shielding gas, and because it produces the stable arc, and of course, the contaminated are the with the less oxygen level, the contamination with the oxygen is less using this type of the shielding gas. In case of gas metal arc welding process, we can use normally commercially we use the carbon dioxide, but difficulty of the carbon dioxide, that carbon dioxide can be decomposed into carbon monoxide and oxygen, and of course, finally it actually increases the oxygen level in the final weld joint because of the using carbon dioxide. Carbon dioxide is more commercially used, but we can use the inert type of gas also in case of gas metal arc welding process, but we need to know the stability of the arc under this shielding gas. And shielded metal arc welding, here normally you use the high oxygen level, and because shielded metal arc welding submerged arc welding process, we can mostly find out the high level of the oxygen, because of the we can use the silicon oxide also as a composition in the flux material. So, that is why oxygen level is high in case of the submerged arc welding process. So, apart from all this type of slag or flux or gas shielding gas, it is also possible to combine the different composition of the shielding gas. They may also affect not only the shielding purpose, they can affect the other aspects of the welding. Probably sometimes we use the mixing with the other sealing gas or type of the sealing gas, that mainly on the purpose of the stabilizing the arc, concentrating the arc, that is also, and sometimes we intentionally we use the other oxygen also, and that can be used as a surface active elements during the welding process. So, the purpose of the using sealing gas, not only the sealing of the molten weld pool, maybe to enhance the performance of the welding processes, sometimes best we can choose the composition of the sealing gas, or we can mix the two different types of the sealing gas, or we can mix the oxygen or with the sealing gas, so that with the specific purpose of the taking the effect of the surface active elements and to get some benefit in the surface using the oxygen in the with mixing with the sealing gas. So, if we look into that now gas metal reaction, little bit the chemical reaction in the welding process. So, first the reaction takes place between the gas, sealing gas and the liquid interface or liquid metal. So, the reaction happens between these two, and during this reaction there is a dissolution of the oxygen, nitrogen and hydrogen in the liquid metal. But in basic way we will try to discuss some that how this reaction happens. So, first we look into the reaction between the nitrogen and metal. So, how they react with respect to each other. So, when molten steel is actually exposed to the nitrogen, that results in the dissolution of the nitrogen atoms in the molten pool. So, weight percentage of the dissolved nitrogen at the given temperature can be represented by the Siebert's law. Here we can see the N equal to K into root over of P N2. So, here the K is the some constant parameter or constant term that is called the equilibrium constant term here. So, here you can see that this K can be linked with the other free energy of nitrogen in the liquid state, liquid iron, and that free energy of the nitrogen in the liquid iron can also be represented by this equation. You can see that it is some linear equation with respect to temperature. So, that also follows the Henry's law. So, here delta G actually represents the free energy of nitrogen in the liquid iron, and Pn2 is the basically partial pressure of nitrogen above the molten metal, and R is the characteristic gas constant. So, if we put the appropriate value here, and of course, all this reaction basically we see it is a, we are representing the reaction is as a function of temperature. So, therefore, having the reaction that happens during the molten pool with the atmosphere, that entirely strongly dependent on the temperature. Similar way we can find out the reaction between the oxygen and metal reaction. So, here we can find out that oxygen from atmosphere, and what may be the source of the oxygen. So, one source of the oxygen during the welding process, it comes from the atmosphere, that may be due to the insufficient sealing process. Sometimes in oxyacetylene welding processes, so the excess use of the oxygen in oxyacetylene processes, that can be a source of the oxygen. Sometimes we can use the oxygen that actually containing the inert sealing gas. So, sometimes the sealing gas may contain oxygen, either it is the inherent properties of the sealing gas, for example, CO2, or sometimes intentionally we can mix with the oxygen with the sealing gas. For example, activated TIG welding process, we can use the oxygen with the sealing gas. So, that are the different source of the oxygen generally present in the sealing gas, and here when we use the CO2 as a sealing gas, and we can see the reaction happens at the very high temperature during the welding process. CO2 gas is decomposed into carbon monoxide gas plus half of CO, and if we look in the balance of the equation, and finally it can produce the carbon and oxygen. So, that carbon and oxygen can take part in the can be a part of the carbon, also react with the steel or using the base metal, and it may form the carbide, but oxygen can be a part of the oil metal molten oil pool, but here also the absorption of the oxygen also follows the Siebert's law, and we can see the similar way that free energy of oxygen absorption delta G, that is also a function of the linear function of the temperature. And here we can see the weight percentage of oxygen in the liquid iron can be found out by forming that, again it is a logarithm scale oxygen, and it is also a function of the temperature here also. So, overall that type of reaction, that type of equation can be Siebert's law may be useful here to roughly estimate the what is the amount of the oxygen can be dissolved in the molten pool, or it becomes the part of the welding system. So, overall if we look into that, what are the properties that actually impact in presence that with the presence of the oxygen and nitrogen content. Here the two graphs shows that nitrogen content, how the mechanical properties can vary, and with respect to the oxygen, how the mechanical properties vary, whether it can be used beneficially or not. Now, if we look into the first figure, the nitrogen content, here you can see that nitrogen, with the increment of the nitrogen content with the oil pool, molten metal of the, or maybe the oil joint, we can see that there is a considerable decrement of the percentage of the elongation and impact low by increasing the nitrogen content. But in other way also we can find out that ultimate tensile strength and the yield strength that actually increases with increasing the nitrogen content. So, in that sense, presence of nitrogen sometimes used the beneficially to increase the amount of the ultimate tensile strength of the joint, or maybe the we can if we try to improve the yield strength, then nitrogen is helpful in that sense. But of course, if we look into that oxygen content, here you can see that probably with increasing the oxygen content in the oil joint, that almost all types of the properties actually decreases. Here you can see the ultimate tensile strength, impact load, yield stress, elongation, all actually decreases in presence of the oxygen. So, that means we understand the mechanical properties at all not beneficial in presence the, or if oxygen content is high in this case. So, objective can be sometimes that to avoid the as minimum of oxygen content and maybe, but some moderate amount of the nitrogen, that actually helps the improvement in the at least the oil joint strength in case of the fusion welding process. Now, we can look into the effect of the other components of the oil joint, that is the hydrogen, or how hydrogen and metal actually react, and we can see the first we look into that what are the source of the hydrogen in the welding processes. That first is the presence of hydrogen is told that what is the consequence effect of the hydrogen. The presence of hydrogen in steel basically creates or susceptibility to the hydrogen cracking or cold cracking phenomena can be increased. So, therefore, it is beneficial to avoid the presence of the oxygen hydrogen in case of the oil joint. So, what are the source of the hydrogen here? The combustion products in oxy-fuel welding, the combustion product they may contain the hydrogen, moisture or grease sometimes used on the workpiece surface, or maybe we can find out the moisture in the electrode also, that can be act as a source of the hydrogen also, and hydrogen presence in the workpiece or hydrogen presence in the sealing gas. So, these are the typical source of the hydrogen in case of the welding process, but if you want to avoid these things, we can carefully measure this, that can be reduce the hydrogen level by simply avoiding the hydrogen containing sealing gas, that is a straightforward. Next is that if you the moisture may contain some hydrogen, moisture in presence of moisture is the source of the hydrogen also in the electrode. So, before using that we can dry the electrode and the flux, drying the flux to remove the moistures from that. In that way we can remove the hydrogen content in that type of the source during the welding process. And of course, cleaning the filler wire and the workpiece is necessary also to remove the grease, because that grease chemical, that grease can be act as a source of the hydrogen also. So, therefore, cleaning is required for the workpiece surface. So, that is a safeguard to minimize or to reduce the amount of the source of the hydrogen normally in case of any case of welding system. But of course, presence of the some amount of the hydrogen that also follow during the welding process, simply the Siebert's law. Here we can find out that similar kind of equations here also. So, here we can that all the equations are also given, and here we can represent the free energy in this case, in this reaction also, that depends on the also the temperature and partial pressure of the hydrogen. So, apart from this chemical reactions on the shielding gas and different oxygen, hydrogen and nitrogen, their impact on the weld joint properties, discussing these things. Now, we will try to look into that, what are the slag metal reaction. Basically, presence of the slag, this is also another way of protection of the molten pool, but proper welding flux actually helps to control the weld composition as well as the protect it from the atmosphere. So, dual role can also play using the slag also. They protect the molten pool, at the same time they actually control the final weld composition. So, they becomes part of the weld composition. So, what are the typical type of the slag basically use? The first is the halide type of the flux, such as CF2NF, CF2BaCl2 NAF. These are the typical halide type of the fluxes are normally used, and oxygen free flux is basically this type of the halide flux. We can see that it is oxygen free. Therefore, this oxygen free flux is basically very much helpful for the welding of the titanium and aluminum alloy, because the titanium alloy and aluminum having the tendency to form the oxides, and that is this tendency or reaction rate with the oxygen is more as compared to the other component, for example, other as compared to the steels basically. So, that is why it is always beneficial to use the halide type of the fluxes in case of the welding titanium and aluminum alloy. But other type of the flux, that is the halide oxide type of the flux, CF2CO Al2O3, and this type of the flux is simply slightly oxidizing component are also there. So, this type of the flux is suitable for the welding of the high alloy steel. Oxide type of the flux, that means in this case the MnO and SiO2, so both are having the oxides. So, that type of the oxides is basically suitable for the welding low carbon steel or low alloy steel. So, these are the typical type of the flux basically we choose depending upon the type of material, and here in details to know that what the reactions is happening, this what way the reactions is happening during the welding process, when is the molten weld pool actually interacting with this type of the fluxes. So, some overall idea, basic idea that what type of reactions may happen here. So, oxides in the welding flux, we normally use the welding, these are the types of the oxide flux we use the welding, that is SiO2, TiO2, CaO, MgO, Al2O3 and Fe2O3. These are the typical oxides in welding flux we used, and what are the typical thermomechanical reactions basically takes place. At high temperature, oxides definitely try to produce the oxygen, and SiO2, MnO2 can decompose in the following way. You can find out that SiO2 produce oxygen and MnO also is produce also oxygen, and that oxygen also react with the metals, and they basically titanium, it produce the titanium oxide, and aluminum it will try to produce the aluminum oxides. So, this way that this therefore, ultimately it is always it will try to create the titanium oxide and the aluminum oxide, but welding of the titanium and aluminum, it is better to avoid the using some oxide type of the fluxes, because it is having good affinity with the oxygen in case specifically welding for the aluminum and titanium and their alloy. So, Now, there is maybe the another type of reaction may also happen, that is called electrochemical reaction. So, that reactions occurs at the electrode tip and the slag interface, because that electrode tip and the slag also in that interface, in case of the direct current electrode positive DCEP, direct current electrode positive polarity, or in that weld pool, molten weld pool and the slag interface, that in that case molten weld pool slag interface, in case of the direct current electrode negative is the that reaction is. So, therefore, what we can predict here, that DCEP, direct current electrode positive, when in that case the reaction between the electrode tip and the slag interface is more important, but when using the DCEN polarity, the molten pool and the slag interface reaction is more important here. So, we will try to look into that, what type of reactions may happen here, what type of electrochemical reactions basically happens in this process. So, here you can see the metal actually in case of DCEN polarity. So, metal and the slag, slag is that oxides in the slag, they can form the metallic oxides and produce the free electron. So, that oxides also from the slag, that oxides oxygen in the slag's oxygen, from there the oxygen becomes part of the molten pool and it also creates the amount of the free electron. So, that in case of DCEN polarity, that free electron is basically actually accelerated to go to the workpiece and that actually generate the amount of the heat. So, in that case this is the reaction happens in case of DCEN polarity, but if you look into the cathodic reaction, what is the that reaction. So, first if you see it creates the molten metal, that free electron basically creates the molten metal, that by the reduction of the metallic cations from the slag. So, that free slag also absorbs the free electrons and it becomes it produces the Si. So, this type of reaction is basically is called the reduction of the metallic cations, and that reduction happens from the slag. In other way also removal of the refining of the oxygen from the metal, because that free electron removes the oxides from the oxygen from the metal, and then ions, oxygen ions becomes part of the slag. So, this type of reaction also called the removal or refining of the oxygen from the metal. So, that type of chemical reactions, electrochemical reactions normally happens in the welding process. Now, we come to that, apart from the reaction with the shielding gas, now we look into that, what is that next topic of this module is the residual stress and the distortion. But what way the residual stress may happen in the welding processes. So, residual stress is basically generated due to the welding process. There are several factors. So, one factor may be some metallurgical changes, that means the residual stress may be generated due to the thermal strain and thermal contraction, maybe the volumetric strain, some metallurgical transformation, structural changes and boundary constant, all actually impact is a very complicated way the generation of the residual stress. So, that amount of the stress becomes the final part of the weld joint after solidification of the weld joint to the room temperature, and then as a consequence of the residual stress there may be some generation of the amount of the residual distortion. So, when you try to actually analyze the residual stress and distortion, so that probably look into that mechanical constant that is responsible generation of the amount of the stress, but mechanical constant if you look into that can be explained in the continuum scale, what the microstructural changes, all these things in the microscopic scale. So, that different length scale if we analyze this thing, so source of the residual stress or generation of residual stress can be better explained. Now, broadly in general the residual stress happens due to the in case of material after the solidification, and mainly the change in the solidified structure and any kind of mechanical constant that actually apply during the welding process. And related to that residual stress and distortion generation, that non-uniform temperature change basically happens, that is called thermal strain, and strain it creates, and that equilibrate the amount of the residual stress over the whole body, it is a over the volume of the body. So, not only on the limited to the surface. So, therefore, the typical cause of the residual stress and distortion in any kind of case of oil joint is that non-uniform heating and cooling subject to different position, the heating and cooling rate are different. Difference in the expansion coefficients, specifically it is more serious when you try to look into the two different types of the material. So, there in that case the different expansion need to follow the different expansion coefficients. Mechanical incompatibility of the different types of the components. So, different types of the components, the incompatibility mechanically may also exist. Structural deformation from the metal working. So, already pre-stress or pre-strain condition we use the sometimes for the samples for the welding purpose. So, structural heterogeneity in micro scale. So, structurally it may not be the homogeneous, but in the when you look into the microscopic scale, the structure may not be homogeneous, that also is also responsible for the generation of the residual stress and distortion. And of course, that various before using the welding process, sometimes the material base metal can be sometimes the it follows some various heat treatment process. So, that during the heat treatment process it can also create some amount of the residual stress during the residual stress also, and that materials we use for the further processing. So, that during the processing of the already heat treated surface, they can create the some non-uniformity in terms of the expansion coefficient, inhomogeneity within the structure, and all these are responsible for the generation of the residual stress and distortion. So, if we look into that one how to understand the residual stress, we look into the one welded hand. Of course, this understanding is very specific to the welding process. So, we take a sample schematic picture of the welding process. Here you can see that welding process, the figure we can start weld process, and it is moving along the x axis, and the heat source is moving along the x axis. So, it is a continuously welding for the sample. Now, then we try to look into the different sections at the different time, different section they are having their temperature conditions are different in the different positions, or temperature distribution are different in the different section. So, in the first case, if we look into the section DD, here you can see that section DD, that in this case there is no temperature change, because this is about supposed to join but not done yet. So, temperature distribution, no change in the temperature distribution. So, we can say that there is no generation of the residual stress at the section DD, but before no generation of residual stress. But if you look into that typical aspect of the residual stress, that residual stress actually creates the serious problem. Residual stress cause the serious problem like hydrogen cracking and the stress corrosion cracking. Here we can see that it actually residual stress impact on the hydrogen cracking and stress corrosion cracking, but at the same time it impact the life of the weld joint when there is a more serious, when the weld joint component is subjected to some kind of the fatigue loading condition. So, in that case the residual stress is the more serious problem. So, objective can be reduce or as low amount of the residual stress generation. So, various techniques generally we follow in straightforward way to reduce the residual stress. One is the post weld heat treatment. Most of the cases after doing the welding process we follow the heat treatment process. So, that way that heat treatment process also try to reduce the amount of the residual stress within the body. Then pinning and the vibration, these are the two mechanical processes, and for the stress relief of the weld joint also sometimes followed to reduce the amount of the residual stress. But to do that Now, we will try to look into the what way the residual stress can be generated. That now, if we look into the section BB, so section BB is exactly at the position that is under the heat source at this certain point of the time. So, it creates some molten oil pool, and the behind that it creates the some amount of the already solidified oil pool. So, in that position, what can be the temperature distribution? If you see the section BB, that we can see the temperature distribution is from the center to the maximum is around the center, and then gradually it is decreasing, but of course, it is the molten state, and at the same time the molten pool is separated by the surrounding solid content of the metal. So, that influence the distribution of the residual stress. So, section BB, that heat source, here the sigma x, that amount of the stress along x axis is close to 0, is exactly at the center point close to 0, but further away from the heat source the stress are compressive in nature, since expansion is restrained by the surrounding metal of the lower temperature. So, if we look into further away from the oil joint, the sigma x becomes the tensile, and the sigma x is balanced with the compressive stress areas near the oil pool. So, here you can see exactly center point is the amount of the residual stress is 0. If away from this thing, it becomes compressive in nature, in further away it becomes tensile in nature. So, that tensile is basically balanced by the try to balance the compressive nature of the residual stress. So, that distribution of the residual stress to some extent, the temperature and the what way it is interacting with the surrounding, what is the nature of the surrounding surrounding of the molten oil pool. Based on that, whether nature the type nature of the whether it is tensile or compressive, and their distribution has been decided. Now, if we look into the section CC, the oil metal and the adjacent base metal have actually cooled. So, if we section CC, in that case it is already cooled, and that metal is adjacent, the base metal have cooled, but tendency to contract, that actually produce the amount of the tensile stress. So, here the section CC is already cooled, but the surrounding is not exactly in the room temperature, some hot environment is hotted body is also there surrounding. So, based on that, the stress distribution at the center is basically tensile nature, and the further away from that thing there is a compressive nature, and again it becomes a tensile in nature. So, in that we will try to equilibrate the state of the stress between the varying between the tensile to the compressive. Now, if we look into the section AA, in this section the oil metal and the adjacent base metal already cooled down and already contracted further, therefore, produce the high amount of the tensile stress. So, similar analogy, that at the center is already contracted. So, it creates the high amount of the tensile stress at the center point, and further away produce the further away from the oil zone, it creates the compressive amount of the stresses from the oil zone. So, this is the typical nature of the stress distribution normally happens in case of the oiling process. Now, if we look into that analysis of the residual stress in basically here you can see that longitudinal residual stress, that means simply longitudinal residual stress is the along x axis. So, what is the amount of the longitudinal residual stress, how it varies with respect to transfer direction with respect to y. So, you can find out the sigma x y is a function of the maximum amount of the stress, and here you can find out the distribution. So, the distribution of the stress shows that distribution of the longitudinal residual stress is on the along the oil line, that the center point center it is a maximum tensile, and away from these things it becomes the compressive in nature. So, this is the typical nature of the longitudinal residual stress. Similarly, if you can find out the transverse residual stress, here you can find out that transverse residual stress is basically low magnitude are produced in the middle part. So, middle part transverse residual stress is almost very low magnitude, and balanced by the compressive stress is basically at the end. That is the typical nature of the residual stress, but if the lateral contraction is restricted of the weight joint by some external constant. So, in this case we can find out that uniform tensile stress is basically added. So, all are in similar nature, maybe all are in the tensile strain, tensile in nature, and but the at the center point the maximum amount of the residual stress is basically increases to some extent, but pattern remains the same if there is no any constant applied to the welded plate. So, this is the typical distribution of the transverse sigma y, the transverse amount of the residual stress, and that distribution we are representing with respect to the x direction.